frequencies. So my name is Michael Dobbs, and today I'll be talking about a computer algorithm to probe new physics. So, quick overview of what CERN is. It's a particle collider in Switzerland, and what they do is they smash high-energy protons together. They accelerate them around this ring, and then at the detector Atlas, we have two protons colliding and at very high energies. Also, this is about 10 kilometers in diameter, so it's very large. And what occurs is when these two protons collide, they have very high energy, and there are a lot of products of those reactions that we care about. And those products are made up of these elementary particles. So this is what's called the standard model, or the particle zoom, that all of the particles that we know about are created from these particles. So for example, a proton is created from two up quarks and a down quark. A neutron is created from two down quarks and an up quark, and an electron is created from an electron. So this is an elementary particle that we know of, maybe from chemistry, that constitutes part of an atom. So what we're doing is colliding high-energy protons together. So what's actually reacting or interacting are the quarks in between, and what occurs there is a bunch of reactions and particles flying off that we couldn't see before because now there's more energy. So new particles can be created that couldn't be there prior. And what our job as physicists is to detect these and figure out the properties or the things that go on behind the scenes. So what we have is a detector called the Atlas detector. This is to scale. And this detector is there to measure certain properties of these particles that are flying through here. And this is a diagram of the detector. It's a cylindrical detector, and the particles are traveling through this very narrow strip right here to collide right at the center here, and then all of those particles shower out into the detector. And a cross-section of the detector looks something like this, and here are some particles flying through there. So once a particle interacts with the detector, it can decay into other particles, and those particles that can then decay into more particles, so it creates this shower-like effect, what we call a jet. And there are different parts of this detector to measure different properties and to measure different particles. So for example, the electromagnetic calorimeter is to measure charged particles, the hadronic calorimeter is to measure properties of hadrons, etc. So what I was doing was working on a computer algorithm that was previously made before I came, but I was improving it. The goal of that algorithm is to find B quarks. It's a certain quark that was on that list a second ago. And those are very important because they're a direct product of the Higgs decay, and Higgs, if you haven't heard of the Higgs boson, it is a very important particle that's on the brink of physics right now. It was just experimentally detected or proven to exist about a couple years ago, and it's the particle that gives other particles mass, so it's very important to know more about it, and the point of the algorithm that we have is to find those, because they only occur one every, I think it's billionth of a interaction. So finding those is important. So the algorithm had certain inputs, which are things that the detector measures and then go into the algorithm. So those are the position, the momentum of a jet, or the original momentum of a particle prior to its shower, and the track quality, which tells us how well we know the values that we measure. So the algorithm I was working on was a recurrent neural network. A recurrent neural network is set up much like a brain is, with neurons and signals being sent in between those neurons. So data is processed at the same time. Compared to how past algorithms worked, you did process A, then you did process B, then you did process C. This does process A, B, and C at the same time, much like your brain does, and uses the information that's occurring at process A to finish process C, etc. So it's a little more complicated, but you can think of these lines here as data flows. So this could be, going back to the brain example, this could be a touching the wall or something, senses, and this is a data flow from, in the particle physics example, you could have momentum, position, etc. And once data flows into what's called these hidden nodes, these are like neurons in the brain, it operates over time, and that's like signal processing over time in your brain, and spits out a statistic that you can use to characterize your data and figure out what's happening. And one other important note is that some of these variables, some of these input variables, are very important to some of the statistics that pop out. So each of these lines has a certain weight associated with it, which again determines the significance or importance of the input to the output. So for example, this one has a very high significance. It could be momentum and some statistic that's correlated to momentum. So what we do with these algorithms is we train them, just much like we train our brain throughout the process of our life. So they learn as they process data. So what we do is we give them a set of data points, and they try and approximate the data as best as possible, knowing what they know. So one thing that happens a lot is you overtrain it, and that is similar to overfitting data, so that you get a fit that looks something like this, which has zero error. Goes through every single data point, so there's no error whatsoever. But if you're given new data that follows the underlying distribution, you see that you'll have data points in between, and the errors get very large. So what we want to make sure we don't do is overtrain, i.e. overfit the algorithm to the data that we have, so that when it sees new data, it does a better job of approximating that data instead of only the data that it's given, like in this case. So we need to make sure not to train it too much. This is just a quick graph of what the performance looks like of the algorithm over multiple training sessions. Eventually, once you train it too much, it starts diverging away from what is actually occurring, and we want to stop it right there so that it doesn't diverge and we get the best approximate fit. So why do we use recurrent neural networks to solve this problem? Well, we have easily adjustable parameters for different data. It takes into account correlations between tracks or data that is gotten from the detector, which if we compare that to the previous algorithm, there assumed no correlations between the tracks. And you can think of correlations between the tracks as if one event occurs in a shower, there's a higher probability of a different event occurring, and there's a correlation between them. So also it's easy to extend to more input variables. Like in that diagram we had just a second ago, we can always just add more of these dots. And that is what my project was to do, is to add more dots, or improve the recurrent neural network by finding new inputs to this algorithm that are uncorrelated to past inputs. And so the reason we care about this correlation part of it is because if we have two inputs that are correlated, when you train the algorithm, it doubly learns about that input. We don't like that because that means that the divergence occurs more quickly for those variables than it does for the others. So we have to stop earlier than we could. So what I made is correlation plots between these variables. So one of the variables that I created and wanted to utilize was the fractional momentum. So that is the momentum of a particle, which is the mass of the particle times how fast the particle is moving, the velocity. The mass of a particle divided by the mass of the parent particle, or the particle that came before the shower occurred. And so what we did was we plotted this variable, the fractional momentum, against each of the other four variables that were already there in the algorithm. We can see that there is no direct correlation between that and any of the other variables, so this variable is helpful, and it's not correlated with some of the other variables that we have. The second variable that we were looking at is dr. So dr is what's called the opening angle. So if you think about a particle flying by and it's decaying into two other particles, it's the angle between where those particles are moving. That's the opening angle. And one correlation we saw was with the opening angle and the momentum of the parent particle prior to the shower. There is a direct negative correlation. So you can see that by if we increase the dr by a little bit, we'll overall see a decrease in the jet momentum. So there's a direct negative correlation between the two of them, i.e. if this one increases, this one has to decrease, this one increases, this one has to decrease in order for this equality to hold true. So that's a problem because they're correlated and we don't want that. And this is a great variable to have because it has very high discriminatory power, i.e. if we have two different particles and we have this variable associated with each of them, for different particles, the variable dr is very different. So it has high discriminatory power between two different particles that we're looking at. So we really want it here. So we came up with a fix for it. So the problem with the correlation is that it doubly learns about the variables. So what we did is we artificially cut half of the data that was given. Not in total half of the data, but cut half of the information that the algorithm learned in the process of the iteration. so that it had the same amount of information as the other algorithms did. And that actually ended up giving us some good results. So this is a graph of the, I guess I'll explain the axes here, the B-jet efficiency. So this, the x-axis here represents, given a particle that is a B-quark, which is what we're looking for, how well do we identify that as a B-quark? And the y-axis is given a particle that's not a B-quark, something we don't care about, how well do we reject that, i.e. not say that it is a B-quark when it's not. So in essence, the area under this curve, or under any of these curves, is how well we did. How well we tag the ones that we want to tag and get rid of the ones that we don't want to. So the previous algorithm was IP3D, which had this curve right here. The recurrent neural network prior to me coming is this brown line, so you can see there's a little sliver right here, and that it's a logarithmic graph in the case that each of these lines is 10 times the last line, so it's not linear as it is, so it's a little more area than it looks like. And after me coming, and after the reweighting that we did, we get this blue line right here, which is above the brown line, and that accounts for about a 1.5 times non-B-jet rejection increase and about an 8% tagging efficiency increase. So, in conclusion, we have a new method, recurrent neural network, for finding, or for identifying particles, and I ended up coming up with 2 different variables that we could input into the algorithm and get a better approximation to the data. So I wanted to thank my advisors at CERN, some of the professors here that helped me through the process, a student that I conversed with, NSF for the funding, CERN for putting up with me, Sonoma State for being my home institution, Fresno State for sending me there. And I also have some pictures of me going through Europe afterwards, and this is me working. Lots of coffee involved. Thank you. Any questions?
Yeah, it's a little bit confusing. What you're doing here is they're having these collisions, thousands of collisions, right? And your algorithm is going through the data looking for interesting collisions, right?
Yes, exactly.
Okay, so that's why you're trying to find something where the particle that you want is going to show up, and let the computer find it for you. And then when it has a whole bunch of candidates, and then somebody looks at it and says, hey, yeah, this is interesting.
Yes.
Okay, so that's
we're looking
the
for
purpose of the algorithm.
Thank you, yeah. Yeah, looking for interesting events that are occurring, specifically ones with the B-quark, because that's highly related to a particle that we don't know much about.
Yeah, I did some work at Stanford Linear Accelerator Center, so I was thinking, well, maybe people aren't understanding exactly that that's what is going on here. We're looking for the interesting events.
Yes, yeah, thank you. Yes?
What time was that taken in front of one of these?
Very early in the morning. There was a rush. It's actually very surprising. When you get there right, well, actually got there about 30 minutes before the Louvre opened. There was already a line way out. But getting in there, everyone's literally running to this painting. So I was in the rush over there. Thankfully, I'm a runner, so I have a good mile time. There was no one in front of it. It was front and center.